Dear students, welcome to session 6 of module 3. So in today's session we will discuss about steady state errors and error constant with respect to feedback control systems. Now coming to the outline of my presentation today, I think the first 5 topics has been discussed in the last 5 sessions, and in today's session we shall discuss about steady state errors and error constant, which is one of the important concept that we are supposed to understand with respect to any system, because when we try to analyze any one of the system, the major problem that we come across is the errors in the result. So it is always necessary that we need to take necessary measurements to avoid the errors that can occur due to the malfunctioning of the elements or due to external factors. So we will now check what are the types of the errors that we can come across when we give any input for a second order system. So we'll try to analyze the steady state error for the system using different types of input in today's session. Now coming to the introduction part. So as I told, any control system inherently suffers from steady state errors in response to certain type of input. That is what I told you. When some kind of input is given, there is a chances that due to some malfunctioning you may have some errors in your result. Okay, so these systems may have no steady state error to a step input, but the same system may exhibit a non-zero steady state error to a ramp input. That means the error what we are going to get from a system varies from input to input, right? So if there is no error for one input, for example, for steady state error input, if your system is not giving any error for another type of input like ramp or parabolic signal, there may be a chances of errors that may occur during the analysis. So whether a given system will exhibit a steady state error for a given type of the input or it may not give an error, it basically depends upon the type of the open loop transfer function of the system. So the basic occurrence of a steady state error in for any system, it is basically determined by the transfer function of that particular system. So we'll analyze how these steady state errors can be evaluated from the open loop transfer function in the upcoming slides. Basically, when we consider the classification of any control systems may be classified according to their ability to follow the step inputs, ramp inputs, parabolic inputs, and other type of the inputs which we may give for a system. And also the magnitude of the steady state error due to these individual inputs are indicative of the goodness of the system or performance of the system. Now let us consider a unity feedback control system with the open loop transfer function, which is given as g of s is equal to, so this is the open loop transfer function what I have, which is given as g of s is equal to k into t a s plus 1 t b plus 1 etc up to t m s plus 1 divided by s to the power n t1 s plus 1 t2 s plus 1 etc up to tps plus 1. Okay, so here the denominator gives you the location of poles and numerator gives you the location of zeros, as we have understood, and k is considered to be the gain of the system and t is considered to be the time constant, right? So this transfer function, it involves the term s to the power n in the denominator, which represents the n poles at the origin. So this term, that is s to the power n, it indicates the number of poles that we can have in the denominator, right? Now similarly, we can classify the systems as type 0, type 1, type 2 system based on this capital N value, that is the number of poles which we have in the origin. Based on that, we can classify the system as type 0, type 1 and type 2. For example, if I do not have any pole at the origin, then it is considered to be type 0 system with n as equal to 0. And similarly, if I have one pole at the origin, if this n is 1, it indicates that you have one pole at the origin, then it is considered as type 1 system. Similarly, if I have two poles at the origin, which indicates that n is equal to 2, it is considered to be type 2, type 3 and so on. So we are classifying this systems as type 1, type 2, type 3 based on the capital N value. So I hope this concept is clear. So this you need to remember, because we will be dealing with these type of the systems in the next upcoming slides. Now, as the type number is increased, the accuracy also improves. Okay, this is one thing what you need to know. But however, increasing the type of the number aggravates the stability of the system or disturbs the stability of the system. So we need to have a compromise between steady state accuracy and relative stability of the system. This is one thing what we need to know. So we cannot just go on increasing the n value so that we are going to achieve more accuracy. No, that is also not possible, and we can also cannot decrease the type of the system so that I can increase the stability. So we need to have a compromising relationship between the steady state accuracy and stability of the system. This is one thing what we need to take care. So we should have a compromising relationship between type and stability of the system. Now coming to steady state errors of an unity feedback system, we'll try to analyze the stability for this. Now let us consider a system which is shown in the figure. So here, as you can see, R of S is your input, right? So E is the error signal. So this is your error signal, and G is your open loop transfer function, and C is your output. H of S here is considered to be unity. Because it's an unity feedback control system, I have taken H of S to be as equal to 1, right? Now for these type of system, the open loop transfer function is G of S, and the closed loop transfer function is given as C of S by R of S is equal to G of S divided by 1 plus G of S, because H of S is 1. So this is the closed loop transfer function what I'm taking for an unity feedback system to analyze the steady state errors of the system. So let's evaluate the E of S value for this type of a system in the next slide. Now here, let's analyze the steady state error for a unity feedback system as told. Now as we know, when we simplify the transfer function, the error signal E of S, right, the transfer function and the error signal E of S, when we correlate, we can take E of S by R of S as equal to 1 divided by 1 plus G of S. This is because, see, if you can observe here, I'll just draw and show you. This is your error detector signal, right? So you're taking here, this is your, okay, I have my R of S here. This is your error detector. Output is taken as E, correct? Now we need to get an expression for E of S. So R of S is this input and H of S is 1. So you have a feedback from here. So G of S is fed as here. This is here G of S because H of S is 1, correct? So E of S is nothing but equal to what? The difference value which we are going to take, correct? So when we simplify for this, you are going to get E of S by R of S as nothing but equal to 1 divided by 1 plus G of S. So this is the error signal that we are going to get for the system. So using this particular expression, we can find the E of T value for a system. So let's see how we can do this. Now using the final value theorem, we will try to evaluate the error signal value here. Okay, so since you have E of S by R of S as equal to 1 plus G of S, if I cross multiply my R of S here, you can observe this, E of S can be written as equal to 1 divided by 1 plus G of S into R of S. So the final value theorem actually provides a convenient way to find the steady state error performance of any stable system, which we'll be applying it now, right? So let's take the steady state error by using the final value theorem, which states that ESS, that is steady state error, E represents error, SS represents steady state. So steady state error is symbolically represented as ESS, and this is taken as equal to limit t tending to infinity E of t. Okay, now if I take this into a Laplace domain by applying Laplace transform, I can write this expression as equal to limit s tending to 0 of s into u of s. This is nothing but the statement of your final value theorem, Laplace final value theorem. Now according to this, if I write my expression, so my steady state error can be written as equal to this value, that is limit s tending to 1 s into r of s divided by 1 plus g of s. Now this is the expression what we have for the steady state error. Now we will try to find out the steady state error for different inputs, that is for different value of r of s. That is what is our task now, right? I hope this is clear. Now let's find the error for different inputs. Now the static error constants what we have for a system, okay, so they are nothing but the figure of merit of the control system. So higher these constant values, the smaller will be your steady state error. Also, for a given system, the output may be usually considered as a velocity, pressure, temperature, position, and so on, right? So we shall now consider the output error that we can have for a system by taking position, velocity, and acceleration, right? So let's do this now. Now first error constant that we are evaluating is known as position error constant Kp. So here input is taken to be an unit step input. So the error value that we are going to get for an unit step input, it is usually represented as static position error constant and it is denoted as Kp. So as we know, we have the expression for E of s as equal to what? Limit s tending to 0 of s into r of s divided by 1 plus g of s. Now since I am taking an unit step input here, so since unit step input is taken, you can take r of s as equal to 1 by s. So I will take this to be 1 by s. So that is why here we are cross multiplying r of s and it is taken as 1 by s. Now we will try to find out the value for this error constant, that is steady state error constant. You can observe here that this s and this s is getting cancelled. So numerator s and denominator s, they will get cancelled and we can get the expression for ESS for a unit step input as equal to 1 divided by 1 plus g of 0, because I'm eliminating my limit and I'm taking this to be g of 0, so that your position constant Kp is nothing but taken as equal to limit s tending to 0 of g of s, which is nothing but equal to g of 0, and you can write your steady state error as equal to 1 divided by 1 plus Kp. So try to remember this expression. This is very important. Kp is nothing but taken as equal to limit s tending to 0 of g of s, okay, and I'm replacing this g of 0 with Kp so that my error constant ESS, steady state error constant, is nothing but taken as equal to 1 divided by 1 plus Kp for a unit step input. So you need to remember these two expressions. These two expressions are very important to solve the problems. You can get a questions on this. Now coming to the next part, that is we will try to evaluate the Kp value for type 1, type 0 and type 2 systems. Now for type 0 system, your Kp is taken as equal to limit s tending to 0, your open loop transfer function, standard open loop transfer function, which gives you the value as equal to k. See, when you replace s with 0 here, you're going to get Kp as equal to k itself. Similarly for a type 1 system, okay, so it is taken as limit s tending to 0, k divided by s to the power n value is 1, so you're going to get the value as k divided by 0, which gives you the value as infinity. And similarly for type 2 system also, the same thing holds good. You will get the Kp value as infinity for the type 2 system also, correct. Now coming to the steady state error for these type of systems, steady state error for a type 0 system is taken as 1 divided by 1 plus k. This expression, this is the error for your type 0 and this is the error for your type 1 system. ESS is equal to 0 because your ESS is nothing but equal to 1 divided by 1 plus Kp. So it is 1 divided by 1 plus infinity. So all of you know that 1 divided by infinity is nothing but equal to 0. So for a type 0 system, you have a finite error value, but for type 1 or higher system, the error rate is going to become 0. That is with Kp, with position constant Kp by taking input as unit step. Now we will take the next type of error constant, which is named as static velocity error constant. Here the steady state error of the system is found using the unit ramp input. So for that purpose we are taking E of s as equal to limit s tending to 0 s divided by 1 plus g of s into 1 by s square. So when you apply the limits, so one of your s here, it gets cancelled, they'll get cancelled, and you're going to get the value as limit s tending to 0 of 1 divided by s into g of s. This is my error value. And if I take my static position error constant kv, which is defined as kv is equal to limit s tending to 0 of s into g of s, by replacing it I can write my steady state error ESS as equal to 1 by kV. So this is the value that we have for the steady state error with velocity constant kV for an unit ramp input. Okay. Now let's analyze the error value for type 0 and type 1 using kV. Now for type 0 system, we are taking the same expression, that is limit s tending to 0 of our open loop transfer function. So it is going to give you the value as equal to 0, because in the numerator you have s into k, so it becomes 0. For type 1 system we have kv as limit s tending to 0 of s into k, your zeros divided by s into your denominator. So what happens here is, here you will get this s and this s will get cancelled, and all these terms are going to become 1. Okay, this is also 1, this is also 1, and this is also 1, so that you are going to get kv value as equal to k, right? And when we analyze the error for the system, the error value depends upon your kV value, and similarly for a higher order system, for type 2 system, kV becomes infinity. So just remember these three values, that is kV value for type 0 system is 0, for type 1 system it is k, for type 2 system it is infinity. Now similarly, when we substitute for the error value, error ESS in terms of velocity constant kV is nothing but equal to 1 by kV, so it is taken as infinity for type 0, 1 by k for type 1, and 0 for type 2. Now the next part, we will take an example of an acceleration constant, static acceleration error constant, which is represented as Ka. So this is the steady state error of the system for a parabolic input. As you know, the Laplace transform of a parabolic signal, unit parabolic signal, is always taken as 1 by s cube. Now by replacing this 1 by s cube here in place of r of s and simplifying it, you know that this and this will get cancelled, you will get s square here in the denominator, so that you can write ESS as equal to 1 divided by limit s tending to 0 of s square g of s, wherein this is nothing but taken as equal to your acceleration error constant Ka. So Ka is now represented as limit s tending to 0 of s square g of s, right? And now if we write the expression for ESS in terms of Ka, it is taken as 1 by Ka, right? Now coming to the value of Ka for type 0 system, Ka is 0 for type 0 by applying the limit, and for type 1 system it is also 0. For type 2 system you are going to get a finite value for Ka, so it is taken as equal to k, and for higher order system it becomes infinity. So for type 0, type 1 system, Ka value is 0. For type 2 system it is finite value, which is nothing but your DC gain. Ka is infinity for the higher order systems. And similarly, if we evaluate the error values for the acceleration error constant, ESS is 0 for type 0, ESS is 1 by k for type 2, and ESS is 0 for type 3. And this is the table which is showing you the summary of the type of the input and the type of the error values that we can have. So for a step input, for a type 0 system it is 1 divided by 1 plus k, and for ramp input the error value is infinity, and for parabolic input also it is infinity. For type 1 system we have an output value, that is a constant error for ramp input. For other two input it is 0 and infinity. For type 2 system we are going to get a constant error value 1 by k for parabolic input. For other two inputs it is 0. So you have to remember this table to find out the steady state error and error constant values for the given system. Okay, now let's take an example and we will understand how to find out the error constant values for a given open loop transfer function. So as you can see in the question, a block diagram is given with an open loop transfer function and you are supposed to evaluate the static error constants and also the expected steady state error for the three inputs, that is step, ramp and parabolic input. So g of s is here is given as, this is our g of s value, open loop transfer function, h of s is 1. Alright, now we will try to find out the constant values and the error values for this open loop transfer function. So let's do it. Now, for the above example, you know that if we can consider it is a type 1 system, if it is s is equal to 1, and if it is type 0 system, then you will not have any s value, but here in the denominator we have s square, so type of the system is 2. So you know the type of a system is nothing but indicates the type of the errors that we can get. So here for this particular system, since it is a type 2 system, we are going to get kp value as infinity, kv value as infinity and ka value as equal to 10.4. And ESS is nothing but equal to 1 divided by 1 plus Kp, which is equal to 0. And in terms of velocity constant, it is 1 by Kv, which is also equal to 0. And in terms of acceleration constant, it is 1 by Ka, so you are going to get the value of 0.09 for the above example. Okay, so let's see how we can evaluate it. It is 100 into s plus 2 into s plus 5 by s square into s plus 8. That is what I told you. It's a type 2 system because you have the order, power of s as equal to 2 here. Correct? So kp is nothing but equal to limit s tending to 0 of g of s. So if I replace that here, you are going to get kp value as infinity because in the denominator you have s square. Though you may get value for the other terms, since you have s square in the denominator, kp becomes infinity. And similarly, kv is taken as s into g of s. So if I multiply s, one of your s will get cancelled, right? So this is going to get cancelled and one s remains here. So since you have one s in the here in the denominator, you are going to get value divided by 0, which gives you the value as infinity again here, right? Now if I consider ka, it is nothing but equal to limit s tending to 0 of s square g of s. So if I replace it, this s square and this s square gets cancelled, and after that if I replace s with 0, you will get some k value as equal to, here as equal to what? So see here, this is the replacement what I'm doing. So wherever you have s, I'm putting it as equal to 0, so s square is cancelled, so ka value I'm getting it as equal to 10.4. This is how we can evaluate the static error constant values, and using which we have found out the error values for the system. Now this is another example wherein a mechanical system is given and its response is also given here. Okay, so we need to determine the value of m, b and k for this particular response curve. So let's take one more example. So here a mechanical system was given in the previous slide and we are supposed to find out mbk value using the given response, right? Now using the final value theorem, we can take x of infinity to be as limit s tending to 0 of s into x of s. So since here we have the value of your x of s as an input with a steady state value, so you are going to get the x of infinity value as equal to 2 by k, which is nothing but equal to 0.1 feet. So this is another practical example wherein we will be using the steady state error values in order to evaluate uh, the actual parameter values such as mass, spring value and the dashpot coefficient and so on. So I'm ending my session for today. So as we know, today we have discussed about steady state errors and error constant, and we have seen how we can evaluate the steady state error and error constant value for different types of a system. And you know that we are able to analyze the different types of the system based on the number of zeros that we have in the origin. So I hope the session was interesting. So these are the reference book which you can refer for a few more problems and you can solve it. Thank you all. Have a nice day. Jai Shri Gurudev.